In a previous video, we looked at Dedekind's axioms. That's the foundation for the set of natural numbers. Okay, so Dedekind isolated this number 1 that's a natural number, and he looked at a function s defined on the set of natural numbers with values into the set of natural numbers. He called it the successor function. Okay, that is a one-to-one function. So it has this property here. All right, and also n is not a successor. All right, and also the set of natural numbers has this additional property. For any subset of it, A, if A has these two properties here, okay, then A is the set of natural numbers itself. Okay, given this successor function, we realize that we can write S of n to be just n plus 1. All right, so this is what Dedekind considered. Now, let's see if there is anything else we can get out of these axioms here. All right, so in order to do so, let's assume that P is a sentence. Okay, and this sentence depends on the set of natural numbers. Okay, so what does that mean? It means that we can associate a truth value, true or false, to P of 1, P of 2, P of 3, and so on. Okay, now let's assume we can do two things with this sentence P. So the first thing is we can verify that P of 1 is true. All right, and the second thing is that we can say that if n is some natural number, okay, and if P of n is true, then we can prove that P of n plus 1 is true. All right, so let's assume we can prove these two ideas for this sentence P. Okay, and then let's look at the following set. Let's say A, let A be the set of those natural numbers n with the property that P of n is true. Okay, what can we tell about A? For example, we assume that we just proved that P of 1 is true, right? So P of 1 is true, which means that 1 is in A. So 1 is an element of A. Also, we actually said that we were able to prove the second statement. So if n is in A, okay, n being a natural number that is in A means that P of n is true. Well, so P of n happens to be true, then we prove that P of n plus 1 is true. What does it mean for P of n plus 1 to be true? Well, if we look back at A, okay, P of n plus 1 being true means that actually n plus 1 belongs to A. So actually us proving these two statements equates to 1 being an element of A, and with the fact that if n is in A, then n plus 1 is in A. So now actually if we go back to the third of Dedekind's axioms, we just figure out that A, our set A here, has these two properties. All right, which means that A is equal to n. Okay, what does this mean? A is equal to n. Well, let's look back at the definition of A. A being equal to n means that P of n is true for any n that is a natural number. Well, actually what we proved is a very important idea. Okay, so we proved that given some sentence that depends on the natural numbers, okay, if we are able to prove that P of 1 is true, and given some n, a natural number, if P of n is true, we can prove that P of n plus 1 is true. All right? From Dedekind's axioms, we can say, well, P of n is true for any natural number n. All right? So this idea is called mathematical induction, and it is a very important method of proving the fact that certain sentences that depend on the set of natural numbers are true.